Welcome everyone, and thank you for joining us for this fourth webinar of the year. I will be your host today, and Jan will be the speaker. So just a few words about us. I'm the manager of the business development at Amherst Technologies, and Jan is the CEO. Amherst Technologies, just in few words, it started 25 years ago. Can you just please directly go to the next slide, and then I will introduce the subject of the presentation and all the information. Yes, perfect. Just a few words about Amherst Technology, just to give you a quick overview about who we are. Amherst Technologies, we are based in Brussels. We are essentially a technology provider. We have a few technologies in our background, but the main one is the thermal desorption. We are inventing and patenting all the new technologies. The team is between 50 and 60 people. The goal is to be 70 in few months, and we have already done 80 projects worldwide. The business model, the main business model of Amherst Technologies is to be a technology provider. So it means that to associate to local partners to make sure that we can carry out together the different projects. So today, the subject of the webinar will be, we will focus on the energy considerations. And we will more spend time comparing the dig and dump technologies and the thermal desorption technologies. Or just personally, I find it totally crazy that we put the dig and dump technologies as a remediation technologies. It's just moving the contamination from point A to point B. But anyway, that's something every time we are doing an opportunity and we are doing, we are submitting something, we are a kind of competition against dig and dump. But that's really important to compare apple with apple, and Jan will spend time just to understand the basics and to understand more precisely in terms of energy. Just before letting the floor to Jan, some few practical information. The first one is the webinar will last between 30 and 40 minutes. The idea is every time you have a questions, please, you are mute, so feel free to ask it in the discussion, and I will make sure that during the presentation to interrupt Jan and to make sure you understand and you can follow up properly the presentation. After this webinar, you will receive a certificate of attendances and also a file that contains all the questions you might have during this presentation. So thank you once again for joining us, and Jan, the floor is yours.
Well, thank you, Aurélien, and good afternoon and good morning to all of you. Yeah, the subject today, I mean, as Aurélien said, we're having a series on thermal, and in particular, we're having a series nowadays on energy. So I'll just briefly introduce the subject, in particular, what has been discussed about dig and dump compared to in situ, because that's what we are confronted with most of the time. We'll dig into the actual numbers, how much energy is needed, how we account for energy losses, what can we do to it, and then we're comparing ISTD to other alternatives just regarding energy, and finally get to some conclusions. And again, Aurélien can interrupt me whenever you like.
And I will do it, definitely.
In situ versus dig and dump, I've had this, and I agree with you, surreal conversation very often say, yes, but we will only do in situ when we cannot do dig and dump. I mean, that is a conversation I've had in the early 90s, which made sense because in situ was really at the beginning, was not really working or was not proven, etc., etc. But now the fact that I see that we still have this conversation today, it's mind-boggling. So let's see
Yeah, it's making sense.
how and why and how come that people still recommend it. It's the most applied quote unquote technology in intermediation. Why is that? So and a quick illustration about the concept of circular or linear economy. We all have a mouthful about circular economy, but what does that mean for our business? Linear economy is primary use, soil for whatever use it is, or say my shirt for whatever use it is. I don't need it anymore. I'm just excavate it, send it somewhere else, dump it. That is the definition of linear economy. And I take some new soil, which I bring in, same thing. I don't need my shirt anymore, I throw it away and I buy a new one. That is linear economy. We all agree that this is not the right way forward. So we need to do something to that.
And just for understanding, can you explain why is it an issue to do that?
Because we know that we have limited resources. So the whole issue about the whole point about having a circular economy is try to reuse our resources rather than to continue to consume resources we have in a limited amount. That's what we try to do for everything. So we need to do that for soil as well.
Okay.
But now when we get into how to become circular, how to reuse soil, we have 3 levels. The first level is, okay, I will continue to excavate. I will still hold my soil, but I will go to a recycling facility, soil treatment facility. And then that treated soil can still be reused. It is circular now because you bring it back in place, but you still have all the excavation in the hole. That's what I call it level 1 of circularity. The level 2 of circularity, we now go on site. You still excavate it, you still treat it, but you don't transport it anymore. It's a higher level of circularity, right? Mm-hmm. And last but not least, that's what we're going to talk about today. Just don't excavate. Why excavate? Just treat it in situ. That's the third level of circularity. You could argue the final level is just don't contaminate the land. Mm-hmm. We all agreed, but we deal with some legacy. Now, let's get into the comparison. Just, ballpark 30,000 feet comparison between dig and dump and in situ. Dig and dump, as I just illustrated before, is the textbook definition of linear economy. Mm-hmm. It is, and why is it? It's because it's easy to manage. I'm only concerned about the boundaries of my site. I have a problem, I throw it away for the next generation to deal with, and then I buy some new soil and I put it in. My problem is solved. Mm-hmm. That's why it is so popular. But it had many failures. Often I hear, yes, but at least we know what to do. No. It's probably the technology that had the most failures, that had the most issues with stability, with nuisances, with traffic, noise, odors. I mean, it's not certain. It's not technical. It's not issues free. It is not that easy. It's easy to explain, but it has many issues and many risks with it. And last but not least, and that is something I refer to in particular in Europe, because we have a soil health directive, it destroys totally soil health, right? We're talking about soil health. You cannot destroy more soil health than dig and dump. That is the total perfect destruction. So by all means, it's not something that when you see it, you would want to do. Mm-hmm. Why do you do it? Well, because I've always done like that, right? So now, if you look at in situ, whether it's thermal in situ or other in situ technologies.
Excuse me, just to understand why people always have done like that.
Because I mean, when I started in the early 90s, it was the only thing available. Okay. That comparison, they had a big difference. Is dig and dump, you could guarantee the result on your boundary. In situ could not. So it's not like there was an alternative. It was the only game in town. It was the only alternative. 30 years later, plenty of in situ technologies can provide the same result as dig and dump. Okay. But that's why it started. And then, of course, once you start there, you still have a bunch of people who say, yeah, but I do that because I've always done that. Right. Okay. So it's like any innovation, it's hard to bring to the market because say, oh, have you done it before? Or at least dig and dump, we've done it. We know it's failing. We know it has all these drawbacks, but the devil is better. Mm-hmm. But let's go to in situ. It's the textbook definition of circular economy. You take away the contamination and you leave everything inside. It is a little bit more technical, of course. It requires more engineering, but it has shown over time way less failures. You almost have no stability issues. You have little traffic, no noise. You don't excavate the whole thing. You don't disturb the surroundings. And last but not least, you maintain soil health as much as possible. You deal with the contamination, but the soil usage is still maintained. You don't take it out. So,
and just for the last one, even if we do thermal desorption,
Yeah,
you can maintain it.
let me just go to the
Okay.
few next slides, and I'll show you what
Perfect.
I mean. But the question you always have, in particular with thermals, it uses a lot of energy. Yeah, that's true. It uses some energy. As you can see here, and I'm pretty proud about that, over the last 25 years, you see how much energy, and that's the light blue one, for hydrocarbon soil, typically 250 degrees, the amount of energy in kilowatt hours per ton has been steadily declining. And we'll get to that later, how we got there. Same thing for less low temperature thermal, which is like chlorinated solvents. But then in yellow, in a dotted line, you see what dig and dump consumes as energy. And you see that it's also declining. Of course, trucks and excavators are getting a little bit more energy efficient, but it's not as steep. And right now, we're almost at the same level. And for low temperature, we're even way below that. These machines don't run on lemonade, as I often say. And as you can see here, this is nice. Though we're going to excavate everything. It is a hell of nuisances, a lot of noise. I mean, you know what that means. We've gotten used to it, but why would we do that? When I say they don't run on lemonade, this is exactly how much they need on fuel per cubic meter or per cubic yard, depending on how deep you go. It's quite steep. In other words, excavating is very energy, requires a lot of energy, in particular if you go deep. The deeper you go, the less efficient you are, so you require a lot of energy. And also, of course, your trucks need also a lot of energy to go. Mm-hmm. There's a bunch of publications also who compare that, not only the energy element, but also the global environmental element. And you see those columns 2 and 3, where you compare excavation and thermal. You see there's a huge difference in overall environmental impact. That dig and dump is having a much bigger impact than thermal, in situ thermal. And even if sometimes you can see it a little bit of counterintuitive. And to get to your question, René, the biodiversity. The project we did 2 years ago, before, just a few pictures before, during thermal, and after, 1 year after. What this tells us is, yes, and to be fair, I was surprised, because I've always been saying, yes, thermal, we're going to heat it up, and you're going to maintain most of the function of the soil, like structural functions, but the biology will be gone.
Okay.
It is not. And now we are studying that, and we could see that the parcel here, the area that has been treated thermally, has actually seen regrowth of local species much bigger than the parcel next to it, where it just had regular growth. And there's probably 2 explanations. There's temperature. When we cool it down, it stays at 30-35 degrees, so at let's say mild temperatures for a much longer period of time, which are the perfect conditions for a boost in bioactivity. And the second one is the fact that organic matter has been transformed in something that looks like biochar, which is also the perfect substrate for biological activity. And no, they didn't die, they just got it, like silent or inactive. And then as soon as the conditions got back in place, it boomed quite substantially. So also in soil health, we can see that we have some nice results.
Do you see this kind of picture, this kind of situation for all your project? I mean, if you are working on the building, I mean, of course, there is no grass, there is no green stuff. But if you're outside, is it something that you are seeing? Even if you heat up the temperature at 300-400 degrees into the soil?
We're clearly looking at that right now, because to be fair, usually when we finish a project, we don't go back a year after. But it seems that now that we're going to look into these projects, that we see this coming up in almost all of our projects, no matter how hot we have been in the heating. Okay. It's really on the cooling down that this occurs.
And it will be really interesting for our next webinar, maybe to just focus on this thematic.
Absolutely.
Yeah.
So let's dig into the theoretical energy consumption. So because the purpose is energy. So what is how will we calculate energy and measure it? From a theoretical standpoint, you just consider that we have to heat up a volume of soil. We will inject heat, and of course, that heat will be in part lost because not everything is efficient, and then the other part will be used to heat up the volume and also to have some phase changes. So there's going to be liquid, there's going to be, and liquid will go into vapor. So that is phase change. So we have essentially those three elements: the phase change, the heating of the solids or the vapors and or the liquids, and then the heat losses that we have. So that's
it's energy balance.
It's the energy balance.
Yeah.
This is the same thing, but with some formulas. I'm not going to dig into that because it's not.
It looks complicated.
Well, yeah, it seems complicated, but essentially it says the same thing, and it puts the exact parameters of soil, water, contaminant, air in that volume. It takes into account the losses we have at the boundary, so the difference in temperature because between the volume you're heating and the volume that is not, the difference in temperature. And of course, in groundwater, there is groundwater flow, so there is convective loss, because if you start to heat groundwater and that groundwater moves, of course, there's energy that is lost to what you want to do. So it's describing the same as what I'm telling you, but in physical formulas. And when we start putting that into, say, a model, we've used a simple model like a 20 by 20 by 6 meters Vadose zone model where we're going to start to do some calculations. We're going to consider it's a soil matrix. We're going to consider some target temperatures. Why is target temperature important? Once it is defined, that is the temperature at which we will mobilize our contaminants. And as I said a little bit earlier in the introduction, if you have chlorinated solvents, your target temperature will be low, towards 90, 95 degrees. If you target, say, dioxins, it will be much higher. If you target hydrocarbons, it will be like 220, 230, 250 degrees. So the nature of the contaminant will determine your target temperature, which then will determine your energy balance. And the target temperature is there to extract the contaminants. That's what we're trying to reach. So we're trying to reach a certain level of temperature, and then we're done, essentially.
Okay.
So what is important to note is the energy requirement is completely independent of heating techniques. As you know, you can heat with gas burner, with biogas burners, with electrical heaters, with biodiesel burners, with solar panels. You could heat with whatever. It's the amount of energy. It's kilowatt hours or joules or whatever energy unit you use, but it is independent of how you get there. So we're going to focus on energy. We also figure that the only thing that will determine how much energy you need is the soil characteristics. Soil in a broad term. Type of soil, its water content, and as we'll see, that will be the main one, the contaminant content, and the hydrogeology, so the water flow.
Okay.
So the convective losses.
When you say the soil type, I mean, you are talking about the
clay,
yes,
sand, and it is linked to water content. If you look at really deep into clay and soil and sand, is not that much different in calorific capacity, but it is because clay has more water usually than it.
It will influence water content.
Yeah, absolutely.
Okay.
So in a perfect world, let's say we want to go from 10 to 300 degrees. So take an extreme case. We want to consider that in a Vadose zone. So we'll consider the closed circuit. There's no incoming or outgoing water. We'll simplify the model in this first exercise. We consider a pretty standard 35% porosity. So that's the percentage of void versus the per cubic meter. So they're pretty common, 1/3 of void. Pretty standard also density, 1.8 tons per cubic meter, 16% moisture. Now we calculated the energy required. So in a perfect world, this is the volume you have. This is the consider. How much energy do you need to get from 10 degrees to 300 degrees?
And you use the formula of the previous.
Exactly, the one I showed you before. We run it into this, and whether you call it in joules per cubic meter, or in BTU per cubic feet, or in kilowatt hour per ton, which is what we usually do, this is essentially where you get 188 kilowatt hour per ton. That is in a perfect world. So here you have all the, for those who are interested, with my good associate and friend Hatem Sadawi, who published this with all the inner constants and parameters that are needed to get to that conclusion. So that is essentially let's say that's the base model. We're going to consider that as a base model.
Okay.
Now, if you dig a little bit deeper into this, I split it into 3 elements. And you can see here.
So you use the
say the 188 kilowatt hour per ton.
Okay.
We're going to split it.
Yeah.
And we're going to split it. See, the light blue, 17% is 17% of that energy of the 188 is needed to go from 10 to 100 degrees.
Okay.
Oh, sorry, 27%, sorry, is needed to go from 10 to 100 degrees. Then 55% is needed to evaporate the water.
Oh, wow.
Okay. And then only 17% of it is needed to go from, say, 101 or 100 to the target temperature, which in this case was 300. Gives you an indication how important that water content is.
The more water, the more energy
consuming. In this case, the model was 16%. You can imagine if you have half of that water, you're going to shrink substantially the amount of energy needed. If you have more water, you're going to substantially increase.
And this one was for 16% or
16? Okay. 160.
Yeah. Okay.
You can also see here the energy density, but forget about the energy density. Look at the colors of the different pipe. We just kept everything the same, and we went from 5% to 20%. Exactly what you were saying. What if the water content grows? You see, for the same, say, 2 meters interdistance, you go from 30 days to almost 80 days. All things being equal, just because there's more water. So I think you can already see how important water is into the energy calculation and the energy balance. Now, that is part 1, a perfect world in theory. Now we're in the real world. So in the real world, yes, we do have losses and we do have inefficiencies. So we have losses, 3 main categories of losses. We have the energy production. So energy production is, yes, if you need 1 kilowatt hour, it will take you more primary energy to get that 1 kilowatt hour to be actually delivered on site, right? Then you have the transfer efficiency. So if you have 1 kilowatt hour here, how much of that, what part of that 1 kilowatt hour will be actually transferred to the soil? There is some inefficiency there as well. And then we have the boundaries. I'm heating this, there's going to be losses at the boundaries, at the top, at the bottom, on the sides. Mm-hmm. These are the main inefficiencies, which are the case in the real world compared to the theoretical world. So energy production, it's mostly conversion. It's typically something you will have. If you use electricity, of course, electricity that doesn't come as electricity, it's not a primary source. Mm-hmm. So it needs to come from somewhere. If it comes from, say, if you produce it on site because you have a generator, you're going to have 30% efficiency. So you're going to need, of 1 kilowatt hour of primary energy, you're going to have like 0.3 kilowatt hours actually deliverable. If you take it from nuclear, you're going to have like 35% or something like that. If you take it from renewables, you could go higher depending on how you calculate. For gas turbines, now we are at 60%. So that is independent of us. Yeah. It will largely depend on where you are and what you have available as electricity source and where it comes from. So not much we can do about that. Now, of course, we're going to talk about the transfer efficiency, and then the boundaries. Essentially, boundaries. It's a volume. You remember, there's the sides, there's the bottom. There's nothing you can do about it. It's hard to insulate unless you have some specific cases. At the surface, you could definitely insulate it. And then the second one on the boundaries is the convective loss if you have moving groundwater. So if your groundwater moves too quickly, you're going to have a lot of losses. If it doesn't move too quickly, you're going to have less losses, and you can see how you.
Yeah, it's depending on the exchange in surface around it, of course.
And sometimes you can work on that, as we'll see. You can work on that to minimize that by putting some measures in place, hydrogeological containment, so that it doesn't move too much and you reduce your loss. Mm-hmm. So let's talk. The one I forgot about the transfer or skipped was the transfer efficiency to the soil. When you use electric heaters, you have the highest transfer efficiency, about 95%, right? But remember, that's where you have the lowest efficiency to produce the energy. So in total, it will still get you in the about 30%. Now combustion heat. When I started with individual burners, like before 2010, we had 35.
Sorry to interrupt you. So for the electrical heaters, you are writing 95%.
Yep.
But this one is just if you take a look just on the project. Yep. But for the society, it means
no.
What's the yield?
Go back to what I said before. You have the first loss, which is how to produce energy. So if I have 1 kilowatt hour of primary energy, I will have 0.3 kilowatt hour of electrical energy. Okay. out of that 0.3, 95% can be transferred to the soil. That's what I'm saying.
Okay.
So out of 1, you go to 0.3, and then you go to 0.27.
Okay.
Right?
Okay.
Now, in the case of, say, natural gas, you have no loss into the primary step. So natural gas will be delivered as such. So you'd still keep your 1 kilowatt hour. But then with very old burners like we had only 35% efficiency. Most of it was just lost at the transfer. We could only transfer 35%. Today, we can transfer 85% to the soil. And that's one of the justifications how this got so steep. The reduction in total consumption is in major part due to the fact that burners are more efficient than they used to be. So that in transferring their primary heat or energy into heat to the soil, that's where it comes from.
And do you think we could increase this efficiency with the burners?
Yes, we could probably go, but as you will see, going from 35 to 85 is a huge step forward in consumption. So going from 85 to 95, it's marginal. At some point in kilowatt hours per ton, it doesn't make more. At some point in time, you reach that kind of maximum. You'll see that the research we're doing now is much more focused on making sure that you don't have to heat, that you heat essentially only what you need to heat, instead of trying to heat everything. So
okay,
that's the next leap of gains we can make. So energy, then the losses at the boundaries, I just want to focus on that because there is a lot we can manage to that. It's of course, it's proportional to heating time, and it's proportional to temperature gradient. So the difference between the volume we're heating and then the outside part. So that difference will drive how much loss you have. Same thing is your loss when we heat this room. The temperature outside and the temperature inside, the bigger that difference, the more losses we'll have through the walls and through the roof, etc. So as you can see, the longer it takes to heat, the more losses we will have in kilowatt hours per ton. It makes sense because, of course, it's a function of time. And by the way, losses are expressed in kilowatts, so in power, and that is seen very clearly. The second part of groundwater flow is that we illustrate with a model where you could see a certain velocity of groundwater flow, and then you can see heating some area, and I don't know if it's clear on the screen of everyone, but this is the area that is heated, and here you can see the temperature. So you can see that from left to right, you can see that core of energy moving away from the heated zone. So having that part heated, you'll see that like the upstream part of it is not heated very well because that's already gone. So that's a very important element. And you can see it even better into this one when the velocity is like twice as high on the right-hand side and on the left-hand side. It just goes faster. At some point, you can't heat it. It's the same thing if you wanted to heat this room with 2 windows open and a lot of wind going through it, right? It's good. It's the same thing. Now, how to minimize losses? Of course, we're going to insulate. Whatever we can insulate, it's better. Same thing. This house, if we put insulation, we're going to reduce the consumption. And we're going to talk about speed and energy density. There's also a way to, if you can't insulate, to also reduce consumption by increasing speed or energy density. Insulation, you can do it in situ at the surface. There's no way you can do it on the bottom or on the edge unless you start to do some hard work, but mostly you can't do that. Now, and regarding speed and density, of course, we'll see how we can increase the energy flow into the area. In other words, if you want to heat this room, you can have 1 heater or 2 heaters, or you can have 20 heaters. And you will see that if you have 20 heaters in this room, you'll use less energy to reach a certain temperature. Of course, you'll use more heaters, but you'll use less energy. Because even if the window is open, you'll reach that target much quicker.
Yeah, but that's a balance between the investment and the.
We'll get to that right in here.
But I'm following you.
Yeah. So heating. So how to reduce losses? Heating time. Of course, it's the time needed, and that will depend on energy input and on thermal losses. And I take the image of the leaking bucket. What we're trying to do is we try to fill a bucket. And of course, we try to fill it with water, which is what we call here energy. We try to put energy in that volume. And of course, it's leaking. These are the losses at the boundaries of this, or even moving water. That's essentially where the losses come from. Now, in order to reduce the amount of water, the amount of water you need, you can play on the size of the faucet. And if you have a small faucet, small flow, you will consume way more water to fill up your bucket than you have to have a big faucet. That's the image you have. I know it sounds counterintuitive, but the bigger the faucet, the lower the consumption, right? And that's in energy terms what we call power. Power is how big the faucet is, and then energy, which is how much water you have. That's the kind of image I keep.
Yeah, it's a powerful picture to understand it.
So you can relate to more easy stuff.
I will explain it to my grandmother later.
Exactly. You can do that, then you go. Now, how big can the faucet be? It's only it is limited because there is some physics. The soil cannot take more energy than what it can, about say 1 kilowatt per meter at the beginning, a little bit more, but that's essentially how much dry soil can take. So if you put a huge faucet, it would just spill all over. So at some point in time, there's also a limit to how much you can put in there. So we're going to work on here is an example. We have a big interdistance. This is a project we had about 5 meters interdistance. You see the heater wells here. Here's one heater well. Here's another heater well. Here's another one. But 5 meter interdistance compared that to 1.5 meter. That's the difference in energy density. Needless to say, this will take about 30 days. This will take about 6 months, right? So that's needless to say. And you can see it here also. The closer the wells are from each other, so the more to the left you go, of course, the more power you need in kilowatt. You need, of course, much more power in order to heat to bring it. It's the number of heaters you need. Okay. Or the size of the faucet, if you will. But also now look at the losses. The more the more your heaters are spaced from each other, the higher the losses, of course. And you see it starts to play from 2.5, 3 meters, and then it goes up. So the total energy needed, instead of having 200, you're more than doubling the amount of energy between 1.5 and 5 meter interdistance. So having your wells closer to each other reduces your amount of energy. That's what I was explaining. So how do we do the optimum? Optimum is not just energy, and optimum is also drilling cost. Because you can say, yes, but if I have, why not put a heater every 10 centimeters? Yeah, at some point in time, it's going to cost you a lot of money on equipment costs, on drilling. It's going to cost, of course, the scaling is important, and of course, installation, labor, etc. But on the other side, your energy costs will be lower. So if you put all that into a big equation, side by side, and that will differ from one side to another, you will try to find your optimum, if cost is the optimum. And some are going up. Costs are going up with density, and other costs are going down with density. So you'll find your ideal density. That's essentially how we do it.
Is that something you are doing for every single project?
It is for every large project. We look into that in order to find the optimum. Okay. I mean, there are projects that are very similar where you have done the math and you know your cost. But if we go into different regions where drilling costs are different, then we can adapt it. And so like higher or lower drilling costs may just change the amount of or the density. You can also have, for example, energy cost, right? Is it extremely cheap or is it very expensive? That will, in some cases, energy is very cheap. You may just say, okay, then I will reduce my equipment cost. So that will depend on one side to another.
In average in Europe, you would say that the optimum spacing would be
anywhere between 1.5 and 3. That's what usually we have. The example I showed you before, it was more in the range of 4.5, 5, because the depth was 30 meters, 30.
It was bloody expensive.
So drilling cost was very expensive, of course. So there, okay, you weigh in your drilling cost compared to your energy cost in that example. Few conclusions. I think I've tried to convey to you how efficient over time thermal has become, and I think it's not just us, but it's the overall the industry that have been making quite a bit of progress on that end. That your consumption can be driven by design. Design is important, as I showed you. The design will have an impact on your total consumption. It can go from you can double your consumption just by design or reduce it by 50%. When energy is produced, of course, it's much more efficient to produce heat on site, so than centralized. Just try to use dig and dump only as a last resort, not as a first resort. And that being said, well, I thank you for your attention. And I think I almost stuck to the timing. So.
Yes. No, it was perfect timing.
Any additional questions?
Also, maybe just to add, first is thank you, Anne, because it was very clear. Just also when you say that something, I just would like also just to push on this information, because the dig and dump only as a last resort.
Yeah.
You are moving the soil, but then it's still contaminated. Okay, just locally. Well, yeah, you change it, but the point is you're moving, and then
absolutely good point. I forgot to mention that when I compare, like currently dig and dump for 6 is about 180 kilowatt hour per ton. That is literally digging 6 meters deep and transporting it 80 kilometers and bringing clean soil from 80 kilometers.
Yeah.
It doesn't treat the soil. So it's a very good point. Yeah, we don't. We're or a little bit below or a little bit above dig and dump, but with a completely different result. Yeah. On the one hand, it is treated. You have taken care of your liability. On the other hand, you have transferred it to your children. Yeah. So it's a completely different approach, of course.
It's important to compare apple with apples. Thank you, Camilla, for the fun questions. I was laughing during the webinar.
I don't know.
She was proposing to drop a nuclear bomb just to have a maximum energy at one location to remediate it. And
it has been done in some islands in the Pacific, so I don't know what.
We have another question which is not related to this directly to the webinar. It comes from the US, so I don't know if it's still in this following this webinar, but it's about have we already done PFAS remediation?
I think there's another webinar that we had, and we're going to do another one on PFAS specifically. So long story short.
Do you have 10 seconds to
PFAS? Can PFAS be treated by thermal? PFAS can be pre-treated by thermal. What has been proven now with PFAS is that we can extract PFAS from the soil and put it in the water and then treat the water, whether it's carbon, resins, or any other water technology for PFAS. What we claim we cannot do, we do not destroy PFAS. We can transfer them, we can concentrate them, mobilize them, but not destroy it. We're working on that quite to try to find ways. But right now, the state of technology is thermal is a good technology to extract them, but not to treat them. But extracting them is already a huge step in concentrating, going from, say, 20,000 tons to a couple of tons. It's a huge step, but you still have highly concentrated PFAS on carbon or on another medium, but not destroyed, no.
Okay. I don't know if there is any other questions? There is one question here. Do you work with electrical heaters, or is it only gas burners?
Well, we offer both, and when I say both, it's more than both. Electrical heaters, it's one option, and then it's gas burners, it's liquid fuel burners, it's biogas burners. You can work with bioethanol, with biodiesel, with many other fuel sources, but they're two different technologies. The electric heaters, it's also conductive. We don't do any resistive heating. It's the same principle. It's conductive. Every time we do the comparison, we just find out that it uses more primary energy. There are cases where we do hybrid, where we propose hybrid, where typically we have a very efficient and cheap renewable energy. To talk about areas where hydro is available, so that would make sense. But by and large, it's the same feeling as heating your house. And we have an energy revolution or trying to transition. We're going for mechanical energy like cars. We're trying to go electric because when you look at it makes sense. But no one is saying we're going to heat our houses with electric heaters. We say, no, we're going to insulate our houses, but that the transition is not there. So we tend to favor, and our clients as well, more the most efficient one from an energy standpoint, and that is usually with energy, which was not the case 10, 20 years ago, because we had, as I showed earlier, we had that issue with the efficiency of transferring energy to the soil, which is now overcome, and so now there is not a lot of reason for us to go to electric energy.
Okay, it was quite clear. There is another part of the questions here. Are the gas burners more cost efficient despite having less efficiency? It's touching the core of your presentation. Yeah. So just if you can just summarize.
Yeah, I address it in the presentation on efficiency. I say it doesn't touch anything. When whether you heat with electric heaters or gas heaters, the amount of energy, once it is transferred to the soil, what happens in the soil is the same. But there is a huge difference in cost, in capital cost. I mean, the cost of a burner is a fraction of the cost of electric heaters and electric panels. So there is also a cost efficiency there. But what happens in the soil is exactly the same.
Okay. Quite clear. I don't know if you have other questions. Please feel free. I will give you still 5 seconds. But Jan, thank you for this presentation. Just because it was every time with Jan, it's quite intense. And so if you want to just watch back this webinar, just please jump on our YouTube channel. You will see all the webinar we have done the last 3 years, and also this one. Once again, you will receive the certificates of the attendance just after this webinar, and we will also send you a quick summary of the questions and different exchanges. So thank you for joining us, and see you next month for a monthly webinar.
Bye-bye. Thank you all.